Hi there, welcome. This is Mr. TG. This lesson is section 2.7 in Algebra 2A, and the topic of today's lesson is absolute value functions and graphs. Now, in front of your notes, your guided notes, you'll see the parent function that we'll be graphing. It's f of x equals the absolute value of x. That's the parent function of all the graphs that we create for this lesson. Now, something to keep in mind about the type of graph that we're going to create, it's no longer going to be linear. All our graphs are going to be forming a V-shaped graph, as you can see in the diagram, and here's why. If we substitute points in for our domain, remember the x-axis, the input is our domain. If we put in -3 into the absolute value, it turns into a +3, -1, +2, or excuse me, -2, +2, -1, 1, 0, 0, and then it comes back again, 1, 1, 2, 2, 3, 3. This creates a V-shaped graph because of the fact that we're always going to generate positive outputs when we put in, even when we put in a negative output. There's also what we call symmetry. This particular graph will have symmetry, as you can see. The input -1 and +1 generates the same output, as do -2 and +2 and -3 and +3. On the graph, we call the midline here the axis of symmetry. It is a reflection line that literally can reflect those points. For example, -1, 1 is right there. If you reflect it over that line, you'll get the second point. So use that. If you're asked to plot points, you can use that to come up with a second point. If, let's say, on my graph I knew this was 2, 2, and I knew that x equals 0 was my axis of symmetry, you could just simply reflect it over here. Another very important term here today is called the vertex. The vertex simply is where the V begins. In this case, it's going to start at the origin, but that doesn't always have to be. But the parent function will begin at the origin. Now, what we're going to be doing with this V graph, this V-shaped graph, or the parent function, is we're going to be moving it around. We're going to be translating it. We're going to be compressing it, and we're going to be dilating it. And there's a lot of different things, or a lot of similarities to the last lesson that they have with these functions. And they are given to you, provided to you in the key concept summary here. This is your parent function. Just like with the functions before, if you look at carefully here, and if we want to move the V up or down, this is called a translation. There will be a number to the right of the absolute value. If it's a plus number, we're moving it up. A negative number would move it down. For example, if I would take this parent function and absolute value of x, let's say if I wanted to add 3, that's simply going to take all these outputs and add 3 to them. And once again, it's going to move it up 3 units. It isn't going to change the shape of the V. It just translates it up 3. So it's pretty simple. If you know the parent function, just simply take and move it up 3, and you'll have your graph of this equation. The next one will show you if it's translated down, it's just the opposite. I'll show you an example of that. Well, I guess I don't really need to show you an example. It just looks like if we're subtracting k. So if you see a number to the right of the absolute value that we're subtracting, you can go ahead and just assume it's going to go down. Other things that can happen to your absolute value function, this one right here, horizontal translations. Be careful with these. What's going to happen, you're going to have an h term. And if it says h minus or x minus h, this moves it right, right that number of units, h units. So it's opposite the sign inside the absolute value. If it's plus, it's going to move it left that many units. For example, if we, let's say we wanted to shift this absolute value function to the left 2 units, we would have to rewrite it as the absolute value of x plus 2, and that would shift our absolute value graph to the left 2 units. It would not change the shape. but it would look something like this. It would go up at a slope of 1 on one side and 1 on the other. And that would be your graph of the after the function's been translated. So again, if it's plus, move it left. If this were minus, move it to the right. And that's basically how you would graph those. So erase this. Now let's go down and review the rest of them. Vertical stretches. You'll notice all the V's so far have not changed shape. There are two things that can actually affect the shape of your absolute value. If there's a term in front of the absolute value, like a number, like A, that will affect it. If A is bigger than 1, it's going to stretch it. It's going to make the V thinner. If that A value is between 0 and 1, like a fraction, like 1/2 or 2/3, that's going to compress it. That's going to make it smaller. And what's going to happen is, if I put in my function, if I would put f of x equals 1/2 times the absolute value of x, something like this, I know right away, based on this A term, that that's going to affect the shape of the graph. It's going to affect all these outputs. It's going to take half of all the outputs that you have here. So half of 0 is basically 0, still 0, but half of 1 is 1/2. Half of the 2 is going to be 1. Half of 3 is 1.5. So you can see how it flattens it out. And then, of course, it's going to reflect over here. And you're going to end up with this compressed V. If this number in front were like a 2, then we would double this. And then all of a sudden it makes it thinner. It would climb at a faster rate. So those are some tricks on how you can actually graph if there's a compression or a vertical stretch on your graph. All basically using the parent function as our baseline to work with. And then this basically says that if you want to reflect it over the x-axis, just make the A value negative. And then the y-axis, the negative x is on the inside. Example of that, if we wanted to reflect, the graph over, let's say, well, let's just do this. Let's put f of x equals a negative x, absolute value of x. All right, since the A is still a -1, it's not going to change its shape. But what's going to happen to my output here is going to turn all the negatives, because that negative is applied after we apply the absolute value. That's how it can be. So if I put 3 in for x and I get the absolute -3 in for x, I get an absolute value of -3, which is 3. And then if I apply the negative after, it's a -3. The effect that has on my graph is it makes it reflect it over the x-axis. As you can see, it goes the other direction. So that's what happens when A is negative. Okay, so I think I've pretty much covered all the different things you can do to an absolute value parent function. They're pretty much summarized here. Now on the next video, you're going to be watching how to graph it by plotting points. And we're going to do some different changes to it, but we're going to basically be using this. So tune in and I'll show you how that's done. Okay, welcome back. Now what we're going to do is actually graph absolute value functions by plotting points. Just to review a little bit, this is the first page of your notes. This is a general form of an absolute value graph right here. You got y equals a times x minus h, absolute value of that, plus k. Remember, the a term right here is going to affect the shape of your graph and the direction. If a is between 0 and 1, it will be compressed. If it's greater than 1, it's going to be stretched vertically. This h, if you see an h in there, it may not. If you don't see a minus h, it doesn't go anywhere left or right. But if you do see an h term, that means you've translated it. You're going to have to translate it left or right. And it's always the opposite of what you see in the absolute value. And this, so I always put arrows here. I indicate that, okay, this is going to go left or right. And don't forget, you might want to put opposite in your notes, because it's always going in the opposite direction. The k will translate up and down, and that's as is. You don't switch the sign on that one. And the a affects the shape of it. The vertex, we always call the vertex H and K, and we will always continue to do that throughout this course. Common variables for those. And the axis of symmetry is simply x equals whatever the H value is. That's that vertical line that goes through the middle of your V. All right, let's go to work and let's graph this function. Now, as you can see, we're dealing with an A term that's negative 1/2, and there is no H term, and there is a 2 outside the absolute value. I know before I even begin that this graph is going to be translated up 2 units because of the 2. It's going to be it's going to be compressed by 1/2 because of the fraction, but it's also going to be reflected over the x-axis. So it's going to be pointing downward. Now, what you need to do with this is figure out where you are going to start. We call that the vertex. So we'll plot points here, and we're going to start by finding the vertex. The vertex is located at 0, 2. Now, how do I get that? Basically, I looked at what's inside the absolute value. There is no H value, so this means we're not translating left or right at all, so that's going to be 0. Here's our up and down translation, that's 2. And that's the first place I start. So we're going to go up to 0, 2, plot a point. Now we know that this graph will be compressed and going downward. Here's how you can find points. Simply plot points. So we can put 1 in. And what that means is you're going to put 1 in for x. Take the absolute value of 1. Negative 1/2 times 1 plus 2. And then that is going to give us negative 1/2 plus 2. And that's 1 and 1/2. So if I substitute 1 in for x, I'm going to have 1 and 1/2. So that's right there. Now the nice thing about absolute value graphs is that they have reflection symmetry. So I can plot a point over there, which is at negative 1, 1 and 1/2. So you get 2 for 1 here. You get 1 point. You actually get 2. If I do another one like 2, substitute it in, show the work over here. We got negative 1/2 times the absolute value of 2 plus 2, which becomes negative 1. 2, absolute value 2 is 2 times the negative 1/2 is negative 1 plus 2 is 1. You can see it fits right into my graph, and then of course you can reflect it over this side, and that's going to be another point at negative 2, 1. Okay, a couple things here. Make sure this vertex 0, 2, think of that as your H and K. That's a common list of variables. There's no H term, so we call that 0. And then 2 is your K value. That's this number. And then go from there. And then connect the points like we did. Notice it has been compressed. It was moved up. And it's going the other direction because of the negative. So there we successfully graphed an absolute value graph by plotting points. Now it's your turn. I would like you to try and graph number 2. First, look at it in a way that, okay, ask yourself, what's happening to my V? Is it going to be compressed? Is it going to be vertically stretched? Is it going to be translated? What's happening? So, and then try and plot some points. But remember, find your vertex first. And I'll let you work on that for a second. Okay, welcome back. As you can see on your list there, I've completed the graph, and I want to just go through and explain it. This is by plotting points. A couple things you should be aware of. If the A value is 3, that's going to make a vertical stretch going up. As you can see, the graph is doing that. There is an H term, and it's always opposite of that H term for your vertex. So as you can see, I've taken that down here and made my vertex x-coordinate negative 1. It's essentially what makes this into a 0. And then this is your vertical stretch, negative 4. So as you can see, I started at negative 1, negative 4. And now I plotted points. I put 0 in, for example, and I always put 1 in either above or below the vertices x-coordinate, and then find out what that is, which was a negative 1. And then I did the same one on the other side because we know I have symmetry. So if you will go over 0 and negative 1, you can just reflect it over here. So you get 2 points for working out 1. and then I did 1, 2, and I've got that point and I reflect it over. So you end up with your graph. It's vertically stretched. It's no coincidence that the slope is 3, just like this is 3. Your axis of symmetry, the red line here, that's what it's called, axis of symmetry, has an axis of symmetry of x equals -1. Be aware how you describe vertical lines. You use the variable x equals wherever it hits the x-axis. Okay, so hopefully that went well for you. Now we got just a couple more problems here. I'm going to push pause, and now I want you to try and come up with a vertex of this problem, and then I'll show you how to do that. Okay, welcome back. I've completed the graph here. A couple things about this graph you should be aware of, and I put this in here just so you can see it. Sometimes when we're presented with a coefficient of x that's on the inside of the absolute value, that's at -1/3, that's going to affect our slope of our V-shaped graph. As you can see, it does compress it. It's not going to make it go downward, even though this is a negative, because we're on the inside of the absolute value. So it becomes a little more challenging to graph this graph. Here's how you start. Find the vertex. And the way I did that first was I set whatever is equal inside the absolute value, make that equal to 0. I did that down here and solved. That gave me the number for the x value. So you can see my work here, how I solved it. The number to the right of the absolute value is still your y-coordinate. If you don't see the presence of a number there, put 0. Then as you can see, I basically plotted points. I put 3, and the reason I skipped by 3 is because I knew that I was taking it x times a -1/3. So remember when I did that down here, like for 6, it's a -1, but the absolute value makes it +1. Just like 0 becomes +1, 9 becomes 2, -3 becomes 2. As you can see, this particular absolute value graph is compressed. It's going upward because the negative coefficient is on the inside of the absolute value. So keep that in mind. But a big thing here, if you can't find that x-coordinate, just set what's in I call it the guts of the equation. This right here, that's what I'm calling the guts. What's inside the absolute value. Set that equal to 0 and solve it, and it will always give you the x-coordinate. The number to the right of the absolute value will always give you the y-coordinate. Now let's go down for our last example. We're working backwards. What I'd like to see you try and do is come up with this equation, and take a moment to do that. Okay, welcome back. Hopefully you had luck with this problem. I started it here for you, and I'm going to finish it. If you're trying to come up with the equation of the V-shaped graph, the first thing you got to find is the vertex. That's this point right here. That's labeled as H and K. And then simply put that into your general form of absolute value graph. So here we go. Let's make this. So we got y equals x minus a -2, which is your h, plus 1, which is your k. And then this becomes a plus a +2. Hence, if you do the opposite of this, what's inside the absolute value, you'll get -2. We see that this is not, basically, you can think of the a as the slope of one side of your v. This has a slope of up 3 and over 1. So that is what a is. So look at the positive side of your v and just determine what the slope is, and that's going to be your a value. That's as easy as we can make it. So there's your equation. Make sure you have this in your notes available. You're just replacing the a with the slope of one side of the v, the h with the vertex is x coordinate, and the k with the y coordinate of the vertex. All right, well, good luck with this lesson. Thanks for listening to this video. Okay.